Bonjour à toutes et à tous. Merci Monsieur Bloom pour ces mots gentils. Sans prendre plus de délai, I would like to invite Professor Siegel. We're honored to have Professor Siegel here with us today, and he's Vice Chairman and Professor of Radiology of the University of Maryland, also a Professor of Computer Sciences also in the University of Maryland. And he will be talking about a subject that has been keeping us awake for quite a few time now. And I think we're very lucky to have him here today. Thank you. Professor Siegel.
Thank you. Let's see if I can figure out how to start. So in any case, thank you very much for the honor to be able to kick off the conference. I can't think of any time ever in radiology where there's been so much excitement and so much fear about a topic other than artificial intelligence and machine learning. And what I'd like to do is talk a little bit about some of the hype, some of the myth, and the reality of artificial intelligence. I'd like to dedicate my talk to a couple of folks, but many residents and physicians throughout the world have emailed me. And in fact, medical students throughout the United States are being told not to go into radiology because they're being told that radiology is only going to be a specialty around for just a few years. And so there's a significant existential threat associated with the idea of artificial intelligence and radiology. And I'd like to talk about that and talk about why I don't believe that at all, and also talk a little bit about what's exciting and what's really interesting about AI and how I think we're going to be able to use it. So this is from one of many representative emails. This is from a resident from radiology in Portugal, first-year resident. And he essentially says that he's contacting me because he's not sure whether or not to stay in radiology because he's heard that the future of radiology is bright, but that radiologists may be replaced in a few years. And this is another one from an Italian second-year resident in radiology, Andrea. And like Zhao, she also has some significant concerns. She wants to know whether she should switch to interventional radiology to ensure a long career. And I can't blame Andrea and Zhao for being concerned after everything that people are reading in the press lately about artificial intelligence as the fourth industrial revolution. And whether it's The Economist or Time Magazine or the Wall Street Journal, everybody is talking about AI, and radiologists are frequently the subject of the profession that could be replaced by AI. Elon Musk has said we need to regulate AI before it's too late. He says, with artificial intelligence, we are summoning the demon. And Ezekiel Emanuel at the American College of Radiology in the year 2016 gave a keynote that essentially said AI was one of the biggest threats to radiology. And in an article in the journal of, in the New England Journal, Emanuel suggested that radiologists may be replaced by computers in the next 4 to 5 years. And Jeffrey Hinton, who is a professor at the University of Toronto and a Google employee, essentially went so far as to say, if you're a radiologist, you're like Wile E. Coyote in the cartoon. You're already looking over the edge of the cliff, but you haven't yet looked down, and there's no ground underneath. And his actual words were, they should stop training radiologists now. And finally, a CEO of a well-funded and well-known startup in Silicon Valley a couple of years ago essentially said that he wanted to get rid of, quote unquote, the wasted protoplasm sitting in front of the workstation that's the radiologist, and replace it with a much better and reliable and consistent alternative in the next few months. Well, he's no longer CEO of that particular company, but there's certainly some of that idea in Silicon Valley. And so Zhao and Andrea, who I'm dedicating the talk to, we're once again being told that we physicians are going to be replaced by computers. And we've been told this many times in the past. And so here you can see an image of what was called the vibratory doctor back in 1904 from the Watling Company. You would put a penny into it, and it would put new life into you. I'm not sure why the doctor doesn't have a shirt or exactly what the vibratory doctor does, but we didn't get replaced by computers or by a machine in 1904. And you're familiar with Hollywood's idea of AI, where once systems become smart, they start rebelling against the humans. Here's Ava from Ex Machina, and here's Arnold from Terminator 2. And so, what is and what isn't machine learning? I think there's a lot of controversy and a lot of different ideas and misconceptions about what machine learning actually represents. So, artificial intelligence is a general term that's been used for many things. One of many techniques within artificial intelligence is machine learning, and one specific type of machine learning is deep learning. And we'll talk about all those. John McCarthy, who coined the term artificial intelligence in 1956, complained as soon as it works, no one calls it AI anymore, which is interesting. And there are multiple types of AI. The type of AI that we have currently is narrow artificial intelligence, also referred to as weak artificial intelligence. So there is an artificial intelligence program that easily beat the world chess champion and could easily beat today's world chess champion in chess, but that same program couldn't beat a 5-year-old at tic-tac-toe. And some examples of artificial intelligence that is narrow include speech recognition, translation, self-driving cars, the Jeopardy match, which was played in 2011, and some of the personal assistants like Siri and Cortana. Then there's general artificial intelligence, and sometimes that's referred to as strong AI or human-level AI. And AGI, or artificial general intelligence, is when the computer is as smart as a human across the board. The computer can reason, plan, solve problems, think abstractly, comprehend complex ideas, learn quickly, and that represents artificial general intelligence. The Jeopardy match was a demonstration of narrow rather than artificial general intelligence. Creating artificial general intelligence is much, much harder than where we are currently, which is narrow artificial intelligence. So when will we get to the point where general artificial intelligence arrives, where we can actually train these systems in a way similar to the way that we train our radiology residents? Well, in a study that was done at the General Artificial Intelligence meeting in the year 2030, in the group, they polled the group about when they thought AGI would finally arrive. And 42% thought by the year 2030, 25% thought general artificial intelligence by the year 2050, 20% by the year 2100, and 2% said never. And so at this point, we're nowhere close to general artificial intelligence. So let's talk a little bit about what is machine learning, because I think a lot of people are under the impression that machine learning is the same as a learning machine, but it's not exactly. Machine learning really refers to a class of advanced statistical techniques that use iterative approaches to solve linear algebra equations, and we'll talk about that in some detail. The vast majority of these machine learning techniques haven't been around for just a few years, but for many decades. And unfortunately, people confuse the term for sort of a smart mini brain that's getting smarter and smarter as time goes on, but it really is more a statistical technique, and let's talk about what that is. Fundamentally, machine learning is mainly about recognizing trends or categories from some data and making predictions and creating a model from those data. It's important to know that there are thousands of variants of machine learning techniques: regression, neural networks, support vector machines, many others. So when we talk about machine learning, there are a huge number of different techniques that have been used for machine learning. Machine learning focuses on prediction, whereas data mining focuses more on discovery of previously unknown data. And Leo Breeman has suggested that because machine learning is so similar to statistics, that it's probably better to call it statistical learning. So one of the things that when we talk about machine, that you should think about is if you have a really complex problem, sometimes the easiest way to solve it is to quote unquote build a machine. When I was a first-year resident at the University of Maryland, they asked me to create the schedule for all the residents' rotations. And it was really complicated because everyone needed to have a certain number of months of certain specialties. Some of the residents didn't want to work with other residents. Some of the attendings didn't want to work with certain residents. And it turned out that it took about 2 months for the residents to create the schedule. And so what I ended up doing is building a quote-unquote machine that just randomly created a schedule. But it created trillions and trillions of them, and then it had the ability to look to see which schedule actually was closest to what was desired. And so even though my fellow residents thought it was a really, really smart computer, it was really, really dumb. It was actually just random, but yet it was able to solve a complex problem by building this machine that created millions or trillions of schedules, and it was able to emulate really smart behavior by being really dumb, but being really fast. Another type of machine that we've built in the past has been one that simulated a radiology department, where we actually had the ability to create a model of patients arriving in the waiting area, going to be scanned, and then we were able to ask questions like, what would happen if we bought an additional CT scanner? Or what would happen if we added an additional technologist? It's not just the speed of the technologist or the scanner, but it really is a complex model, and you have to take a look at the bottlenecks. And sometimes a machine can do a really good job of solving that problem. So here's an example of how machine learning might beat traditional statistics. Let's come up with 5 silly questions, and we're going to try to figure out whether the person answering these 5 questions is a male or female. So what's your favorite color, pink or blue? What would you rather be watching on TV? Would you like to be watching Dancing with the Stars, or would you prefer to watch football? And so the question is, what statistics would you do if you were trying to solve the question of, can we predict whether or not, based on the answers to these 5 questions, whether the person is a male or female? And in doing that, you'd probably try and say, well, what has the highest correlation with male versus female? And then you might create a regression formula. But as it turns out, there may be some combinations that are really unusual. So it may be that we observe that taller women under 200 pounds who prefer blue over pink prefer football, but only if they prefer Star Wars. Maybe there's a tendency for men who prefer pink and are over 200 pounds to prefer Dancing with the Stars. And so the point is that there may be specific combinations that would show up if you created a model, and it wouldn't show up if you did a correlation, or wouldn't show up if you did a regression formula. And so machine learning has the ability to create a model that's able to model for every one of these combinations and then apply that to future predictions. Is this pig an ugly pig or a beautiful pig? Well, maybe you want to look at the eye distance to mouth ratio or the eye distance to nose ratio. But in this particular case, let's assume that it creates this particular pattern where the beautiful pigs are the ones in red in the middle. And then let's say that we had a data set and we were able to essentially just collect data on what was judged to be a beautiful pig or an ugly pig. We humans would recognize this as a heart shape. And a machine learning program would have a really difficult time, a statistical program would have a difficult time of drawing a line or separating the ugly pigs from the beautiful pigs. But a machine learning program could take the data itself and translate that into a formula and would be able to create and derive this formula for a heart. So the bottom line that's really important to remember is what's new is we have the capability of being able to translate data directly into a model or formula. And so if you take a look, here's an example that's closer to CT, where we're looking at nodule size and nodule smoothness and whether or not that's predictive of malignancy. And so as you can imagine, as nodules get larger, And as they are spiculated, they tend to be more likely to be malignant rather than benign. But as it turns out, larger nodules start losing some of their spiculation and the borders become smooth. And so if you had to create a regression model to separate the malignant lesions from the benign lesions, it would be really hard to draw a line or curve. Yet using machine learning in a neural network, it's possible to derive a model from the data that allows you to separate the benign nodules from the malignant nodules. Importantly, there was an MIT study that suggested that part of the reason that machine and deep learning work so well is that most biologic systems follow relatively simple equations. And so I believe that medical imaging, rather than what's been predicted, will actually be the hardest specialty of all to replace within medicine and surgery rather than the easiest one. So many of you may recognize this from Highlights magazine, and it asks the question, what's wrong with this picture? You might be able to find 25 things wrong with this picture, and a 5-year-old kid might be able to find a dozen things wrong with this picture. But there's no computer anywhere that's able to beat a 5-year-old kid at the question of what's wrong with this picture. Asking whether or not there's a TV in the picture, whether there's a spoon and a fork, all of those are relatively easy for computers nowadays. But the question of what is wrong with this picture is a fundamentally different question. And so it's important to remember that that's something that we radiologists do that's different from just determining what's in the picture per se. And in fact, this challenge of figuring out what's wrong with the picture is so hard, it's been suggested in an article in Scientific American in June 2011 as a better test for the emergence of machine and consciousness or general artificial intelligence. And so it's been thought to be better than the Turing test, which was the previous model that said if a computer could fool a human into thinking it was a human, then artificial general intelligence will have arrived. But a harder test might be what's wrong with this picture. And so you're going to hear within machine learning, one of the types of machine learning that has become really popular in radiology and in human vision is neural networks. And neural networks are loosely modeled off of the neural networks in the brain, but in actuality, you can think of it a little bit more like a spreadsheet, a complicated spreadsheet, where the numbers are able to self-adjust to take an input and be able to come out with an output. And actually, our brain works a lot more like a quantum computer because there's a tremendous amount of complexity of the connections, more complexity than in the machine learning models that we have. But inside a neural network, you can think of a complex spreadsheet where each cell in the spreadsheet has a multiplier and an addition value and what's called an activation function, which is not linear. And so every cell is related to all of the cells to the left of it, and it's possible to adjust the multiplier weights and the addition weights in order to optimize the likelihood that the input would result in the output. And then you create a model from the data, and that model from the data actually is used to predict future questions that come up. And the specific type of neural network that we are using in radiology and that's been used for human vision is called the convolutional neural network. That's a neural network where the pixels that are values that are close to each other, say in an image, have a higher weighting than ones that are not close to each other as far as proximity. So one question is, what would happen if we took every single pixel in a picture and made that a machine learning variable? And could we have a computer that would be fast enough to be able to compute that? And the answer is yes. And starting in the year 2012, we started applying these convolutional neural networks and graphical processing units, GPUs, to be able to start intercorrelating all of the pixels in an image. And each pixel becomes a variable. So the pictures that were used to distinguish a cat and a dog, for example, were around 240 by 240 pixels. And even with that small matrix size, you have 57,600 variables. So it was very computationally intensive, but with the GPUs, we had the ability to do that. So you can see here on the right that as the cells, as we go deeper and deeper into the neural network, the computer is able to create identification of patterns. It starts out as edges and simple shapes, and then goes to more complex shapes like a mouth or a nose, and then essentially the computer learns to be able to identify whole faces. And so these deeper neural networks allow one to do things that used to be really, really very difficult because of the use of GPUs. So here's an example where you might have images of the brain on the left, and the output layer would be, is that tumor or is that brain? And all of these hidden layers end up being adjusted in order to maximize the likelihood that the input ends up resulting in the output. And so here's an example of a convolutional neural network where we have an image on the left, and the computer comes up with a probability that it represents that on the right side. And so for Zhao and Andrea, if deep learning has been around since 1943, why all the excitement now? Well, what's happened in the last short number of years is that the ability to be able to recognize what's in an image using human vision has increased tremendously. And so we've gone from an error rate of about 26% in 2011, it dropped dramatically to about 16% in 2012, and then it's dropped now to around 3%. And this incredible ability to be able to determine what is in an image has made computer scientists incorrectly and wrongly concluding that there's the capability of being able to determine what's wrong with this image and to apply it to radiology. But it's a very different thing. And so this supervision that used these fast graphical processing units in 2012 essentially changed the way that we think and changed our approach to machine learning and human vision so that we're using these convolutional neural networks. And so as far as the hype recently, a lot of it's been related to these human vision experts such as Hinton and Andrew Ng and others coming to the conclusion that they'll be able to achieve the same level of success on medical imaging. And so one thing that they need to recall is that there's a fundamental difference between what's wrong with this image and recognizing what's in an image. Also, radiology images are much larger and they're much more complex than the images that have been used for human vision. And so there's some other significant challenges that are also associated with machine learning. But what's happened in radiology now that's really interesting, and we saw this demonstrated at the last RSNA meeting, is it used to take 3 to 5 years with multiple complex steps, such as segmentation, feature extraction, and et cetera, to be able to create an algorithm that would detect disease in radiology, the so-called CAD algorithms for detection and diagnosis. So now what's happened is because we're able to train an algorithm directly from the data itself without going through the complex steps of segmentation and feature extraction, it's much faster and easier to actually create these models from large data sets. And so doing something such as creating an algorithm from data sets might be something that takes a computer hours or days rather than years. So we've got the case in radiology now where it's very easy to create these algorithms, and we're seeing a large number of them that are coming out. The problem is it still takes years to test and validate these algorithms, and it takes even longer for regulatory approval. So we now have a situation where it's easy to create the algorithms, but very challenging, as it always has been, to test and validate the algorithm. So we have this mismatch. The FDA in the US is working on mechanisms to try and speed up the clearance process, but at this point, it's not faster than it used to be. So there's a tremendous backlog of these algorithms that are being submitted and developed and haven't really been tested or validated. One of the challenges also is that we're still struggling with how to test human physicians and trainees for competence. It's hard for me as a faculty member to know when our residents are actually ready and competent to be able to practice, much less computers. And so even if Robbie, the rapid reading radiology robot from 300 years in the future, who could actually interpret radiology studies as well or better than a human, showed up, it might take 10 or 20 years to actually test all of the different modalities, different anatomic areas, and verify that that system actually was able to interpret radiology studies. The other challenge is that there's so many machine learning algorithms, it's very difficult to know which ones to choose from and which parameters to use. And the other question is that to a large extent, there's a black box nature of deep learning. One of the challenges is we know it works, but it's training on the data itself without an explanation of how it works. And this makes many folks who do testing and from a regulatory perspective very uncomfortable not understanding how it works. And because of the fact that they don't understand how it works and the fact that it can also be very brittle, meaning that very small changes can result in significant changes in accuracy of the algorithms. For example, there's something called adversarial examples or adversarial training. So on the left, you can see an image that's classified as a panda with a 60% confidence. But with a tiny amount of additional noise, you get the image on the right that really to our eyes looks identical to the first one. But the computer now classifies it as a gibbon with 99% confidence. And so we're seeing the same thing where an algorithm that's trained on one CT scanner, when it's brought to another scanner, it has some significant difficulty, even though to our eyes, the images look very similar. There's also the question of, can the computer actually recognize all the anatomy in an image? And so I've gone around the world as part of some lectures that I've given, saying that I would wash the car of any algorithm developer that's able to find the adrenal glands better than a sixth grader. And so just recently, Ron Summers at NIH has found an algorithm that has a dice coefficient, which means accuracy of finding the correct pixels, of around 68%. And so because of this, at a debate that we did at RSNA about a little over a year ago, Brad Erickson declared that I should be washing Ron Summers' car because of him having this algorithm that does an okay job of finding the adrenals. But here was my response.
And I'm in 5th grade, and I'm going to find the adrenal gland on a CT scan. I have not seen these cases before. So on here,
he had about 10 minutes of
left
training.
Adrenal gland, and this is the right adrenal gland.
So yay for humans, and I don't think I'm going to be washing any cars anytime soon with this 5th grader, but it really, I think, is a really interesting test of where we are with artificial intelligence, and there are still problems even finding the anatomy. Also, there's nothing close to a general purpose AI system that would allow us to be able to train as efficiently. So our residents may learn from dozens or hundreds of cases and be able to generalize, whereas an AI program may require annotations of millions of cases, and we don't really have the people to annotate that number of cases. But we do have machine learning techniques that have been utilized for decades, and there are tens of thousands, maybe 30,000 very narrow machine learning applications that do a really good job at a very, very narrow task, like fracture detection, brain hemorrhage, multiple sclerosis diagnosis, bone age determination. Many of these things are good and they exist currently. The challenge is, how do you make them all work in concert, and how do you bring them to your workstation? And so part of the main challenge is, how do we find the time and the humans and the money to be able to take these relatively inefficient algorithm training processes that require very large numbers and actually label these data sets? And so there are a number of companies that are springing up working with radiologists to try and label very large data sets, but it's very slow and very tedious to do. So what are some of the most impressive advances in AI outside of radiology and outside of medicine? Well, one of the most interesting ones to me is described here in Nature. It was from the Google DeepMind team. And I don't know if any of you are familiar with the Atari video game system, where there's somewhere around 70 games and there's a joystick and a little red button on the joystick. And what the DeepMind team did was, which was really interesting, is instead of teaching it the rules for all of these 70 games, what they ended up doing is they actually ended up teaching it just to look at the score like a 5-year-old kid might on the screen, and then to just play randomly and learn what creates the best score in playing the game. And so here's an example of the DeepMind's version that only looks at the score, doesn't know anything about the rules in the game otherwise, and just has the joystick and the button. So in the first time when it starts playing, it just moves the paddle around randomly, and it does a pretty bad job. And then after about 2 hours of practice and playing, it actually starts to get really good. Again, it learned all 60 or 70 of these games just by watching the score. So after 2 hours, the system starts playing like an expert, and the paddle ends up coinciding with the ball to maximize the score. And then for those of you who are familiar with the game Breakout, what you may know is that there's a strategy to accumulate points really quickly. And so what ends up happening is after 4 hours, then this magical thing happens where the deep learning algorithm ends up, after playing randomly, ends up learning the strategy about really racking up a lot of points, which is to drill a hole to the back of the wall and have the ball end up knocking all the things out in the back of the wall. And so what happens is the system from then on always learns to drill a hole in the wall. And it learned it on its own by just exploring how to maximize the score. The game of Go was supposed to not be mastered by computers until the year 2030, and there are more combinations than there are atoms in the universe of Go moves. And yet, the DeepMind team was able to beat the world's best player at Go back in 2016. Many of you may not know that recently the DeepMind team created a new version of AlphaGo, which they called AlphaGo Zero, which actually beat the old version 100 games to nothing. Only this version only learned by playing itself, didn't learn by watching human games, which was really interesting. So learning without watching how the humans played actually created a better strategy. And for those of you who are chess players, you may have heard in the last few weeks that the DeepMind team used this similar learning reinforcement technique to play the best computer program, which easily defeats the world's best chess player at chess, and it ended up destroying the world's best chess engine after learning and playing itself for only about 4 hours, which was an amazing thing. This is the scariest bridge in Maryland, which is where I live near Washington, D.C., and you can see kind of the camera careening back and forth. That's not the car, that's the camera. This is a self-driving car driving across a narrow bridge about 20 stories above the water. And the question is, would you trust this car if I told you that it was 10 times safer than the typical human to drive across the bridge, but when it makes a mistake, it makes a hard right turn or hard left turn and takes you right off the bridge? And if we had that question about self-driving cars, how do you debug a self-driving car? And if we had a radiologist and it used a deep learning algorithm, how would we essentially debug that program? And how would we know it was safe? And how would we check it out from a medical legal perspective also? In the Harvard Business Review, they said that what was important and what's really good about computers nowadays is that they're really good at making predictions, but that humans would be needed for judgment many, many years. And one of the questions that came up at the Mayo Clinic is, what do people want in their doctor? Do they want the doctor to be really smart, the top of his medical school class or her medical school class? No, what people want is for their doctor to be confident and empathetic and humane. And one question is, could a computer ever be those things? This is from research that was done at the USC Institute for Creative Technologies.
Hi, I'm Ellie. Thanks for coming in today. I was created to talk to people in a safe and secure environment. I'm not a therapist, but I'm here to learn about people and would love to learn about you. I'll ask a few questions to get us started. And please feel free to tell me anything. your answers are totally confidential. Are you okay with this?
Yes.
So, how are you doing today?
I'm doing well.
That's good. Where are you from originally?
I'm from Los Angeles.
Oh, I'm from LA myself.
So could a computer
When
be
was the last time you
empathetic?
felt
That's a lot
really
more
happy?
empathetic than a lot of radiologists that I know anyway. As far as using machine learning today, one point I want to sort of finish up on is the fact that a lot of the fear and emphasis has been on creating programs to make findings in radiology imaging studies, whether it replaces radiologists or not. But machine learning algorithms and AI are actually really exciting and really very interesting for doing things other than looking at images. So for example, hanging protocols. How do you arrange your MR and CT and other studies on your workstation? There's no PACS that I know of that really does a good job of learning that, and it's hard to explain it to the computer or someone setting it up. But my residents and fellows who watch me as I hang my images learn how I like my images arranged. And so having the computer be able to use machine learning and learn how I hang my images and be able to do that within a few days is something that's really exciting. Speech recognition, image protocol prediction, synthesis of the electronic medical record to show me what's important in the EMR. There are hundreds of applications where we can use machine learning in radiology to tremendously benefit our safety, our communication, and our practice overall. And I think that we're going to be using machine learning in the next few years to make our PACS systems and to make our information systems much brighter than they have been. So to end, Zhao and Andrea, radiologists do so much more than just making findings in medical images. We judge, explain, quality check, counsel, commiserate. We teach and discover and lead and console and do so many things that computers can't even begin to do at this point. So I think overall that for Zhao and Andrea, my advice is finish your residency. Radiology is an amazing and beautiful specialty and career. And my prediction is we're going to need more radiologists rather than fewer radiologists as we move forward. We have decades of work to do before we have a program that can begin to approach doing the reading that we radiologists can. And even if it could, which I think is decades off, then it won't do all the other things that we radiologists do so well. So just to end, humans have been around, if you look at the 24-hour clock of the Earth, humans have been around for around 1 minute and 17 of those seconds. Computers closer to a millisecond, and who knows what's going to happen in the next microsecond. So I mentioned that I had done a debate with Dr. Brad Erickson at RSNA, and I ended up ending the debate by talking about WikiLeaks in a video, and kind of a hypothetical video. If we actually created a video the day after Dr. Erickson, who I debated with about whether computers would replace radiologists, when he proposed his machine learning software to the FDA in the US about replacing radiologists, here's a video of the next day's conversation with the FDA talking about that.
Y me acuesto en su, ya para abrir el restaurante que era el arroz. Y me llama el cocinero. Risita, ¿qué? Ve por la paellera. Venga, que las 2 de la tarde ya están aquí. Mira el bañador, en las chanclas. Todo despeinado porque no me dio tiempo nada ponerme las chanclas y el bañador. Voy a la playa, había subido la marea. Había subido la marea y encontré una paella.
So thank you all very much. It was an honor to be able to give the keynote speech.